Our interpretations of partial derivatives. So recall that the equation z is equal to f of xy represents a surface S, the graph of f. If f AB is equal to c, then there's going to be a point on our surface at ABC. By fixing y is equal to b, we are restricting our attention to the curve c sub 1, in which the interval plane y equals b intersects S. In other words, c sub 1 is the trace of S in the plane y equals b. Likewise, the vertical plane x equals a intersects S in a curve c sub 2. Thus, the partial derivatives of f sub x, ab, and f sub y, ab can be interpreted geometrically as the slopes of the tangent lines at the point ABC, the traces of c sub 1 and c sub 2 of S in the planes y equals b and x equals a. So we've seen in the case in the heat index function, partial derivatives can also be interpreted as rates of changes. As rate to change. If z is equal to f of xy, then our partial z with respect to x represents the rate of change of z with respect to x when y is fixed. Similarly, partial z with respect to y represents the rate of change of z with respect to y when x is fixed. So let's go ahead and look at some of the partial derivatives using a surface that we have already mapped out, and we want to determine, okay, are we going to have, are these going to be positive, are these going to be negative partial derivatives as we go along our function. So for 6, we have the point, negative 1, 2. So that negative 1, 2 is right there. All right. As we go along the x, so the partial derivative with respect to x, so as we're going along x, is our slope negative 1, 2, is that going up or down? And here we have a slope that's going down at negative 1, 2. Our slope is going down on the x-axis, so it's less than 0. Or not x-axis, but as we go along x. Same thing for y at the same point. Is our slope for y going up or down? And looking at it, it's going down. So less than 0. Now, the next two, a and b, we're looking at the partial derivative of x and y, where we took the partial derivative of x first and then y. So what we're doing is we're looking at f of x first at 1, 2. So at 1, 2, looking at x first, it looks like our partial with respect to x, the slope of x as we are going there is positive. Now, as we move that along the y, is it increasing or decreasing? And our slope is increasing as we're going along the y-axis, so that's greater than 0. For b, f of x sub xy, in that negative 1, 2, our slope looks like it is decreasing for x, which we've already said it was. And as we're going along the y-axis, it's continuing to decrease, so it's less than 0. All right, next one, find the indicated partial derivative. So I'm not really going to ask, so for questions like in example 3, I'm not really going to give you those because it's really hard to tell given, three-dimensional shape or surface on a 2D plane, like on a sheet of paper. So I'm mainly going to focus on, are you able to take the partial derivatives? So for example 4, find the indicated partial derivative, and we're going to take it of this function, natural log of x plus the square root of x squared plus y squared. And we're going to evaluate at a point 3, 4. So the first thing I'm going to do is I'm going to take the partial derivative with respect to x. And so the derivative of the inside is going to be 1 plus x squared plus y squared to the 1/2. So 1/2 x squared plus y squared, negative 1/2. Times the derivative of x, which is going to be 2x, all over x plus the square root of x squared plus y squared. All right, I'm just going to clean that up a little bit because the 2's are going to cancel out. So I get 1 plus x over the square root of x squared plus y squared. And in the bottom, I just have the same thing, x plus square root of x squared plus y squared. Now I'm going to evaluate this at 3, 4. So I'm going to substitute in my values. And so I get 1 plus 3 over 3 squared plus 4 squared, square root of that, all over 3 plus the square root of 3 squared plus 4 squared. So I get 1 plus 3 fifths over 3 plus 5, which 1 plus 3 fifths is going to be 8 fifths over 8. 8 fifths times 8 over 1, or 1/8. 8s are going to cancel out, and we're left with just 1/5. All right, that's it for 41. Let's try 48, or example 5. In example 5, we're doing implicit differentiation with our function. So we're going to take the partial derivative of z with respect to x and then with y. And so again, if you recall implicit differentiation, we're going to take the derivative of x normally, and then when we get to z, when we take the partial of that, we're going to show that we took the partial derivative of z. So let's go ahead and start with 48. So x squared is just going to be 2x. So I'm going to go ahead and denote that this is partial z with respect to x. And that equals, so derivative of x squared is just 2x minus y squared. Remember, that's a constant because we're taking it with respect to x of our function z, plus z squared, so we can take the derivative of that, which is 2z partial z with respect to x, minus 2 partial z with respect to x is equal to 0. I'm going to keep all my partial z's on the left side, so I'm going to have 2z, write that as an actual 2z minus 2. It's very easy to mix up your partials and your 2's. Partial z with respect to x, and again, you could use a different notation if you wanted. You could have said, z sub x if you wanted to use that. All right, is equal to negative 2x. Divide, so our partial z with respect to x is just negative 2x divided by 2z minus 2, and I can cancel out that, so I get negative x over z minus 1. You could write that as x over 1 minus z and get rid of the negative on top if you want to as well. All right, so let's see the next one. We'll do partial z with respect to y. And a lot of this is going to work out very similarly. X squared is just 0, negative 2y, plus 2z partial z with respect to y. And let me write that a little bit better. Minus 2 partial z with respect to y over, not over, but equal to 0. So then I'm going to keep my partials on the same side. Equal to 2y. Divide, and so partial z with respect to y is equal to 2y over 2z minus 2. Again, we can get rid of the 2's and get y over z minus 1. And we're left there. All right, so those are our two partials of z with respect